So, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Quantum Mechanics 1 with the course code PHY212, we are at the lecture number 27 and the topic is the time development of state function in the continuous case. In the previous lecture, we have seen the discrete case. In that case, we had the discrete values of eigenvalues for any state function, but now we want to consider the continuum, that is the continuous values of eigenvalues. So, therefore, we would like to develop the time development of a state function for the continuum of the values, and we will see what are the differences between the continuous case and discrete case. So, let us begin. We say that a particle is moving in one dimension. This is one of the simplest example to develop the concepts of quantum mechanics. So, particle moving in one dimension and it has to be in the superposition of energy eigenstates because it is in continuum. The energy eigenstates are so many, you can say, are closely spaced. That is why we say that they constitute a continuum, and then we take its superposition, and this superposition then shall be represented with the help of integral because there are so many values and these are continuous, and this bk is also a continuous variable which depends upon the k, and e raised to power iota kx is the plane wave or the eigen basis or the Hilbert basis which span the Hilbert space. And you can see now the initial state function, by initial I mean when time is t is equal to 0, is expanded in these eigen bases of which span the Hilbert space, and this bk are the coefficients which will correspond to the probability. Now, we can extract this bk out of this integral by just what you can do is to multiply this from the left side with a phi star. Let us call it this one as a phi star, or with e raised to power minus kx over here, and also over here minus kx, and if you calculate then this integral, this will give you the bk value, and on the left side then there will be an integral of psi and e raised to power minus kx. We are interested in these b's because this will give us the probability for finding the processes. So, that is why when we expand the initial wave function in terms of the eigen basis of the Hilbert space, then we are interested to extract back these b's coefficients because from these we will be able to calculate the probability. So, the state of the particle at later time, that is t is greater than 0, because in here we have seen the state of the particle at initial time when t was equal to 0, but now we are interested in the time development of this state function which was written in continuous case, and we would like to know that what is the state of the particle at t greater than 0. So, that usual procedure we will apply again over here. So, this is the time evolution operator which is acting on this psi. So, this is psi 0, psi x 0 or initial state. So, when this will act on it, and you know this is the time evolution operator, and h corresponds to energy. So, this h is the operator, the Hamiltonian operator corresponding to the energy eigenvalue, and when it will act on this h, the b are constants, these will go out, but this h will act on e raised to power iota kx. But this is this equation is actually the time development of the continuous case or the continuous state function from initial state to the final state. So, from in this formula you can see that this final state is after applying this h hat. So, h hat is going here, it acts on k, and we have then I k x minus omega t, and there are these b's coming in. So, this b then, as on the previous slide, we can extract back, and h bar omega h bar omega is coming from the En or Ek. H bar square k square root 2m. So we would like to write them in terms of frequencies rather than energy. So this factor over here, you see, this is in terms of coming from here, h bar omega. So energies are replaced since the h hat is the eigenvalue is Ek, but we would like to write it in terms of energy, in terms of frequency. So this could be write as h bar omega. So that's why you see over here the h bar omega. And since this is the continuous case, you see that kx and minus omega t both are appearing here, and this bk are the probabilities. So there are now many components because and there are many amplitudes corresponding to them. So this bk e raised to power iota k x minus omega t will give us the amplitudes, and we see that the phase of this component is constant. So this is the phase over here. This is constant, and we can calculate it by putting it equal to 0. That is x is equal to omega by kt, and this is the phase velocity is actually can be calculated by omega by t, because if you take this t to the other side, this will become x by t, and this x by t will give you the omega by k, but omega is h bar k by 2m. So this is the phase velocity. So what we are saying, roughly speaking, that you have all the amplitudes like this, and they are oscillating with different frequencies. Everyone has its own frequency. For example, omega 1, omega 2, omega 3 up to omega n, and they have their corresponding velocities, and you can calculate these velocities. But since we are interested, but these are called the phase velocities because every component is oscillating with its own phase velocity. But we will see in a moment in future slides that we will not be interested in the phase velocity, but we will be interested in the group velocity. I mean, if these all components make a one group and it travels with something, so we call it a group velocity. So we will be interested in group velocity with which the whole packet is traveling. So in this continuum case, although this is all the continuous continuous wave functions existing, but we will construct a wave packet out of them, so that the whole wave packet is moving like just like a particle with some certain group velocity. So these components, in these components, those components which have the short wavelength, they will move fast, and those components which have the long wavelengths, they will move slow, because in the short wavelength or the higher frequency, as you can see, and this is the longer frequency, lower frequency or higher wavelength, so their velocity is less than as compared to these one which are moving faster. So every component has its own velocity, but it depends upon the wavelength. There's a famous relation between the wavelength and the velocity. So that's why the greater is the wavelength, the slower is that component moving. As I said that we will construct wave packet out of it. So this wave packet then at t is equal to 0, we will demand, in order to construct the wave packet, and it's very important point to note that we will demand the expectation value of momentum. You can see this is the expectation value at the initial state we are calculating. So this was the initial state. So this is the ket and this is the bra, and this is the formula for calculating the momentum eigenvalue. But remember that this is at t is equal to 0, and we are demanding that this expectation value of p is not equal to 0, which means that it will keep its shape. So imagine that this is the wave packet and it has different frequencies, but its momentum is not changing, that is delta p is equal to 0. When momentum is not changing, then it means that it will keep its shape. So more or less its momentum is constant. By this way it will form a wave packet where different components of the waves are moving or oscillating with different frequencies, are moving with the different energies, but as a whole the wave packet will act as a particle and move with certain velocity, which we call it a group velocity. On the previous slide we calculated the phase velocity for every wave, and for the longer wavelength we found out that the phase velocity was slow, and for the longer shorter wavelengths or the higher frequencies, the phase velocity was high. But here you can see that if we demand that p is constant that is the expectation value of momentum for we demand an initial state is not changing at when t is equal to 0, and it is there, and expectation value is not equal to 0, it is and it is constant, then we form a wave packet. So average momentum of the initial value does not vanish. So it was initially there, so as a wave it is moving, and its average momentum or the expectation value of the momentum is not changing, or it's not vanishing, that is, it's not becoming 0. So the packet, since the packet is localized, we say it is a localized packet, so this psi mod square of the initial state is not equal to 0 only over a small domain. Since it is localized means that it is over a small domain and it acts like a particle. So we giving by constructing a wave packet, giving a particle nature to these waves. So now if it's a wave packet, as I already explained, then we will calculate the group velocity, because phase velocity is for all the single components, but we are interested not in the phase velocities of the single components, but we are interested in the group velocity of the whole packet. And this group velocity is calculated by taking the derivative of frequency with respect to k. So when you take the derivative out of it, or the first order change you take at the k maximum value, remember that after the calculating this derivative, what you do is replace k with a k maximum. That gives you the group velocity. So instead of every packet, every component, let's say this is k1 component, k2 component, and k3 component. So instead of calculating phase velocity for all these components, we calculate the group velocity for the whole packet. So this whole packet which is localized, and this is the formula for the calculating group velocity. So the meaning of k maximum is that amplitude is maximum at k is equal to k maximum. As I said, that when you calculate the derivative, after calculating the derivative, you replace k with a k maximum, so it gives you the maximum amplitude. So maximum amplitude occurs at k is equal to k maximum, and then h bar k maximum, that is the expectation value. Remember that the expectation value of momentum was h bar k, but since we are talking about the maximum amplitude, so the expectation of value will be h bar k maximum, and which will be equal to this, as we have already calculated. And this is the continuum case, because we are calculating from minus infinity to plus infinity, and bk mod square is h bar k dk. Okay, so this is the group velocity. Now if we put things together, if we combine, so here you see that in first term we are calculating the group velocity, but what we can do, actually what we want to do is to know that whether this group velocity is matches the classical velocity or not. So let's say if I have a particle, it is moving with certain velocity, we call it classical velocity, and in the continuum case of quantum mechanics, it has some components in there. And if I calculate the group velocity of them, let's say we call it Vg, whether they two are equal or not, this is our aim to calculate. So Vg is del omega by del k, but we can multiply with the h bar up there and down there, because it's a constant, so it can go inside. So we can write del h bar by omega k. So what you are doing is multiplying with h bar and dividing by h bar. So essentially you are not changing anything, multiplying and dividing by h bar, but this h bar can go inside the differential or derivative. It can go inside the derivative because it's constant, so it will not change anything, and down there we keep it outside. But what then we can do is multiply and divide with again with the h bar square k square by 2m, and h bar by by k, because if we take the derivative again, these things will cancel, and this is equal to this. But why we transform this into this form? The reason is that this is actually the momentum or energy eigenvalue, and then we can write it as h bar k maximum by m, or p by m, because this is momentum, and p by m is equal to classical velocity. So you see that the group velocity and the classical velocity are both equal. So classical velocity and group velocity, we can have wave nature converted into the corresponding to the particle nature, that when many components, many wave components combine together, they form a group, and they move with a group, which and this group velocity actually corresponds to the classical velocity. So this way we see that in the continuum case, when there are many eigenvalues, and we form a continuum, and through the integral we calculate all these continuum, then it forms a group, and when we calculate this group velocity, it corresponds to the classical velocity of the particle. So the packet moves with the classical velocity v by m. Let's move towards an example. It's always interesting to see one example and how these things are working. So consider a beam of neutrons, and in this beam of neutrons, this beam is chopped, producing a pulse of a centimeter long and having n particles in there, each particle having momentum h bar k. So what we are saying is to consider a beam which is chopped. For example, in this figure you can see this is a beam coming in, and by some mechanism you just chop it. I mean you remove the particles in the forward and backward space, and now this is the chopped basis of length a. Chopped means that removing something from both sides. So beam is chopped, so producing a pulse. So it is just a pulse now, not other frequencies or waves are included here, and it's a centimeter long and having n particles. So there are n particles now in this beam. So each particle having momentum h bar k, and each particle is moving with the h bar k. So this is the beam we have produced, beam of neutrons. After the pulse is produced, the initial state of this pulse will be, this is the initial state, psi x0 will be 1 over a under root e raised to power k naught x, because k naught is the initial momentum, and this will be in this interval, that is x greater than or equal to minus a by 2 to plus a by 2. In this interval, the pulse wave function is this, but it elsewhere 0. That's why it becomes a beam, a chopped beam, because we have removed it from the otherwise. So we are keeping only this interval. So in this interval, the initial state of this beam is equal to this wave function. Okay. So next thing is to once we know the initial state function, the next thing is to calculate the coefficients, because from the coefficients we will be able to know the probabilities. So since we have already developed a formula for the coefficients, so you just plug in the wave function and its complex conjugate e raised to power k naught x and e raised to power minus kx, and now it's very simple to make the calculations. As you know, to calculate this integral, if you calculate this integral, this will be sine k minus k naught a by 2 over k minus k naught, and so we now know the coefficients bk. From these coefficients we are now able to calculate the probabilities. So the state at t is equal to later t, that is t is greater than 0. So initial state we already know, we have calculated the probability in it, but now we want to know what is the state at later times. So for later times, psi of x of t, as you all know, that psi of xt is related to initial state with the evolution operator acting on psi naught will produce this one. So this was a psi naught, and when h was acting, so it was producing this omega t over here. So this is the final state, and in this final state certainly h bar omega over here is the h bar k square by 2m, which are the energy eigenvalues corresponding to the Hamiltonian operator. So now we are able to calculate the probability density. So probability density is as you all know bk mod square, but in downstairs you see the integral over b, because it's a continuum case. So in continuum case we want to include all sorts of probabilities inside in this integral. So this sort of normalization, but this is equal to bk mod square if you put it to equal to 1, because it's normalized to 1. So we will have 2 over pi a. So this is the result. Okay, so we are just putting bk mod square, so we are just calculating the bk mod square. On the last slide we calculated bk, now we calculate the bk mod square, which will be equal to this probability. And if you plot this probability, it's very interesting to see over here that it is peaking at the center. So it has somehow the Gaussian distribution, and this is minus 2 pi by a, and this so in this interval see the most probable values lying over this here. So it's kind of, you can see now the localized, so all sorts of frequencies you can see here, but this is sort of localized packet because the frequencies far away are dying out. So it is forming a packet where it moves with the group velocity. So all the having you moving away from here, and you having less and less momentum and less probability to find in these momentum. So particles with these momentums are very less probable, but particles with these momentum are very highly probable. So these particles are moving like a group. So we see that the probability density is constant, that is the state at t later t finds the value h bar k maximum, h bar k naught, and this is the most probable value, and we see that this is constant. So the momentum values are this one, h bar k naught plus 2 by h bar by a, where n from 1 to 3. These are the continuum case, so all probable values, but the most probable value is h bar k naught. It's the maximum value, as you have seen in the plot, that the maximum value was at h bar k naught. And okay, so this was the maximum value we can find, and this probability is almost constant because the most probable value is found there. As we move away, then with the n making greater 2 and 3, there will be less corrections. So h bar k is almost determined from this leading term. Okay, so the number of neurons we can also find out, that what are the delta n, the number of neurons in this interval, and you know that this will be integrated from here to here, k minus 2 k naught over to k, and these are the probability that is b k mod square. In this integral, from this integral we will be able to find the value of delta n, that is the number of particles in the chopped beam. So next important thing is the Gaussian wave packet, which is related to it. Usually in quantum mechanical calculations, we use the Gaussian wave packet. It is very customary to use it because it's not only simple but it's very useful. So let's talk about the Gaussian wave function. So let's say the initial state is this one. So psi x naught 0, this is the initial state. You can see the Gaussian picture already over here. So this is some kind of initial wave function, initial state for some particle. And then what we want to do is to calculate the initial probability. Now we are quite familiar with initial probability. That is the probability at t is equal to 0. This will be equal to psi star psi, and will be equal to 1 over 2. This is the calculation. I mean, you already know the psi over here. Here you already know the psi. If you take the psi star of it, you know this will be minus, and multiply it out, so you will guess this value. The first term will just go away because of the complex conjugation, and then you will be left with this. So this is the probability of initial state, the initial probability, and total probability must be equal to 1. You know this consistency condition, that the total probability must be equal to 1. To remind you that the probability of finding any particle in some packet, so particle can be here or here at different positions, but the total probability must be equal to 1. That's why we say that probability is conserved. Okay, so once we have found the probability, then we want to know the initial uncertainty in position. The initial uncertainty is in the position is equal to the length of this wave packet. So this is delta x, and the momentum is then certain. So in previous lectures we have talked about the uncertainty principle, where we have seen if delta x is constant, that is it is maximum, then a momentum expectation value is determined, and if delta p is constant or it's maximum, then x is determined. So these are conjugate to each other. So here you can see when delta x is a, then the p is h bar k naught. So the momentum amplitude, if you want to calculate the momentum amplitude in this case, so bk would be, what would be, as it's very simple, to minus infinity to plus infinity, this wave function, initial wave function, the Gaussian wave function, you plug in and then you calculate this integral. This is the momentum amplitude, and the square of it is giving us the probability. Okay, so pictorially you can see that when psi mod square over here in x space, you see that the width is a, and the probability, this is the probability, so the width is a, and over here you can see that this is in the momentum space, this is in the position space, and the momentum space from k0 to k, this the width is 1 over 2a. So they will always be inverse to each other. So this is the probability in the momentum space, and this is the probability in the position space. So delta x and delta p Gaussian will be then delta x h bar delta k and h bar by 2, and delta x by delta p minimum will be h bar. So this is the uncertainty principle again invoked here. You see that the delta x, that is the change in position and change in momentum, or you can say the change in the uncertainty in position and uncertainty in the momentum, is the order of h bar. So in this lecture we have seen the time development of a wave function in the continuous case, and we have assumed that we have a system in which there are continuum of eigenvalues. There are so many eigenvalues, they are very close to each other, and we take continuum of them, and then when we take continuum we have to take integrals and for the probability, and we have calculated the probability for this continuum, and we have found out that there are many components coming in with a different phase velocities, but the whole thing become a wave packet. This is a localized wave packet, and the group velocity of this wave packet corresponds to the classical velocity, so it travels like a particle. So although it's we are treating it as a continuum case of all the components oscillating with different phase velocities or moving with a different phase velocities, but when you take it as a wave packet, it's a group velocity. It comes out to be a group velocity which corresponds to classical velocity. And then we have talked about a very practical example of Gaussian wave packet, and in Gaussian wave packet there is always delta x is equal to a, and it is used for because it is compatible with the uncertainty relation. So usually when we calculate in quantum mechanics, we consider our system to be in the Gaussian wave packet or in as a Gaussian Gaussian wave, and we make calculations there, and relatively they are simpler than considering other types of wave functions. So with this, I thank you all.